start chapter 11. Right there. We're not doing the whole chapter. If you get the list, if you download that list that I posted on Blackboard, you'll see that we're doing 4 of them, plus the economic analysis. These 4 right here. Now, if you can remember, going all the way back to inventory, this is what was that, our second chapter, I think, I really highlighted how to recognize which inventory model to use. Look for specific things. The #1 mistake on this chapter, and this is why a lot of students find this to be one of the, if not the hardest chapter, is because it's so hard for them to figure out which one of these to use when reading the story. So get ready. I'm going to give you some hints. And I'm telling you, if there's anything you keep track of right now, it's the hints to determine which one of these to use. I'm going to start with single channel Poisson arbitrary service. Poisson arrival, arbitrary service. This is the only one that the story will mention a standard deviation. And it has to have the standard deviation in the story to be able to do that one. So if you scan a problem real quick and you see standard deviation, you know it's arbitrary service. There's that one. And I put the page number to the formulas you are probably going to need so you can jump right to it. For all 4 of these, trying to make it easier if I can. This is where people start to fall apart in this chapter, and I want to try to give you as much information as I can. Now, single channel Poisson constant service. Constant service will most likely be, it will say something like a robot or a machine or something that provides the same service every single time. And if there's a human involved, it probably can't provide the same service. Almost impossible. So you're looking for the service being described most likely from a machine, a robot. Perfect example would be this car wash. Washes every car in exactly 2.5 minutes every time. This coffee machine dispenses coffee in about 3 minutes every time, or something like that. You'll see where the words are trying to tell you that the service being provided is the same for every single customer. I just thought of the example we'll have. This is our last one, so you'll see it on Monday. But it's an electronic pony ride at the front of Meijer or wherever, and kids are getting on it. When they put their money in, it's the same amount of ride in time for every single child. It never varies. That's called constant service. That's what you're looking for in the description. And there won't be a human providing the service. That's kind of, there could be a human, but odds are very slim to none, because then it wouldn't be constant. So now we're down to exponential. So let me say it again. Standard deviation, oh, this doesn't have a standard deviation, so it's not arbitrary. Constant service, oh, the service is being provided by humans, so there's no way it can be constant. Right? So those 2. So now we're down to 2 of them. And you say, okay, it's got to be exponential service. Now you're looking in the story to see if, at the same time, if service is being provided by only 1 or more than 1, 2, 3, 4. But I want to key in the words. It's not something provides service and then another service after that. That's still single service. You're looking for if there's more than 1 service station, person, whatever it is, providing service at the same time. A movie theater that has multiple ticket places to grab your ticket for any movie. That's multiple arrival exponential service, Poisson arrival. But the key was that there's multiple. So then you go, there's no standard deviation in this problem. There's a human providing service. So it can't be arbitrary, it can't be constant. And it's talking about only 1 service station at a time, or 1 service person at a time. So it's got to be single channel. Because it's not talking about multiple. And that's the hardest 2 of those top 2. Do process of elimination, get arbitrary out of your mind, get constant out of your mind, and now you're down to just the 2 exponentials, And you just have to figure out, is there only one providing service, or is there more than one providing service at the same time? And if there's more than one, you jump to multi-channel. And that's the process you're gonna have to use if you wanna get to the white one fast. Those are your 4 big hints. I went kind of fast. You wanna hear them again?
Yeah.
No, yeah. There's a mixture here. Nathan, you're jumping in? You're gonna do all 4 of them for me?
No, I was just wondering, so
Sorry.
if there's only one guy giving out tickets, would that
One
be a
guy.
single chain?
Why can't there be a female giving out tickets?
Well, that's the point is like,
I'm sorry, just representing.
would the single channel puts on with exponential service?
If
be
there's
just
only one human providing the tickets, it is single channel.
Okay.
Yeah,
But if
it's
there's
not,
more than
it's not
one-
the type of business at all. You're reading to see how customers are getting served, and if there's more than one at the same time. Let me use McDonald's as an example. A lot of times, there's only one cashier taking orders, but then when they get busy, there's 2 or 3 taking orders, so it just went from a single channel to a multi-channel, and it's completely different calculation. So that's what you gotta read. Even though it's the same business doing the exact same thing, is there only one service station doing the service, or more than one? Go, Jason.
So back to the movie theater example.
Movie theater example.
This guy's selling tickets, they're selling popcorn.
Why that
Two
guy?
different services. I said this one.
Okay, 2 different services. This is tickets, this is popcorn. The story's only gonna ask you about one service at a time.
Right.
And if this is the only person selling tickets, and the question's about tickets, it's single channel.
So there's 4 ticket lines.
There won't be 4 ticket lines. If there's only a single channel, there'll be one serpentine
That's
line.
right. That would be the multi-channel.
Now,
Right.
if there were multi-lines with multi-people providing tickets,
It's the
that's
same service too.
the same service, that's right. If this person's popcorn and this person's tickets, and they're the only 2, it's a single service and a single service. If the question's about the popcorn, or the question's about the ticket.
Right.
What was your hint for arbitrary service?
The hint for arbitrary, again, is it will always have, help me,
Standard deviation.
standard deviation. As soon as you see a standard deviation being given in the words, you know it's arbitrary service.
What about for the constant?
Constant, again, it won't have a human. The service will be provided like by a robot or a machine or something. It will even say the words, and the coffee is dispensed the same time for every customer. It'll give you the time, or it'll give you how many it serves per amount of time. Okay, now we got that out of the way. Here's the second thing that everybody has problems with, and that is rate versus time. I forgot to write notes on this, so I'm going to go off the top of my head. But here, I'm going to jump to the point I'm about to make. You have to use rate, but many of these problems will give you time. And you're going to need to convert it to rate. For example, let me think of this. For example, so-and-so who's taking the calls at the customer service desk is spending an average of 2 minutes with every customer to solve the problem, and then the person's on to the next. That's time, how much time it takes to, on average, to serve a customer. To do your calculations, you must turn that into rate. In the problem, it will say, what then will be the average amount of customers served in an hour? So let's turn that, this will be per amount of time. How many is rate? How much is time? You need how many. So if this customer service person is taking care of customers every 2 minutes on average, and an hour goes by, how many customers could be served on average in an hour by that customer service? 30. There's 60 minutes, so 60 minutes in an hour divided by 2 minutes with every customer means that 30 customers, now that's a rate, how many for a period of time. Let me go stay with this 2 minutes, because then it says this customer service person is providing customer service about approximately 2 minutes with each one, but we're going to try to work out the probability for how many per 15 minutes. Hang on a minute, 15 minutes. That's a little tough, but here we go. You gotta convert 2 minutes into how many per 15 minutes? You're all over it. How many? What? 7.5. 7.5 customers are served on average per 15 minutes if it takes 2 minutes on average for each one. 15 minutes divided by 2 equals 7.5. There's the conversion. How do we feel? This is with both arrivals and service. Sometimes you'll be given one of them as a rate and one as time. Sometimes they're both time, sometimes they're both rate. You got to make sure you get them both to rate. If only one's at rate, one's at time, you got to convert that one. And you're going to read on to figure out per what? Per 15 minutes, per half hour, per minute. Here we go. Staying with the 2 minutes, because this is what people do miss this. But it says, the question's all about the probability of this, that, and that per minute. Per minute. How many per minute? Half. If we average 2 minutes for every customer, 1 minute, this is per minute, divided by, is a 2 minute average, means we're helping approximately a half a customer every per minute, because it's taking us an average of 2 minutes. That's how you convert time to rate. Exactly like that. And you're going to have a bunch of these you've got to convert. That's the first step. Once you recognize which one of these to use, then get your rates. Get it in rates. And if you can do those 2 steps, you're going to find this chapter much easier than most people do. Because those are the hardest 2 things. Making sure you're using rates and making sure you know which one to use. Now, go ahead, Jason.
What, is
Is that a question? Just checking.
Is there ever an instance where we use the time, not the rate?
Yes.
But
But I'm not going to put a quiz on there where you're using time. It's a circumstance where you're being, we're kind of heading that way, but it's at the end. Not for any of these though.
Right.
None of these 4, you have these additional topics right here where time's going to be involved. But I only have these at the end if we have time. You know, more questions you ask, the more likely these 2 aren't going to be on there. And these are kind of hard.
Good thing I got another question.
Well, you have these already stats, but I know 90% of you forgot it.
I'm sure.
Right?
What did that give away that it's time and you need to change it? Like when you're reading it.
Every one of these, if it has anything to do with one of these 4, you must.
No, I'm saying when you're reading it in the question.
Yeah.
And you're going, all right, is this time or is this rate?
Yeah, that's the hard
What's to give
part.
away?
If it says, as this customer service rep takes care of customers on average every 2 minutes, that's time. You got to realize. But if it says this customer service person is taking care of customers at about 30 per hour, that's rate.
Gotcha.
So you got to read it. You got to start getting yourself so familiar that when you read this, you can say to yourself, "That's time" or "That's rate." And as soon as you realize it's time, then you got to start converting it to whatever the final question's about. What interval of time the question
Final
about?
questions about.
Yep. All right. Are we ready? I don't feel good. I don't feel the vibe. I'm not feeling it.
You got a bad
Thank
feeling
you.
about this?
I got a bad feeling that everybody's either saying I don't care or I got this so well I don't need to speak up. I hope it's the second.
There's the third one.
All right, here we go. I'm skipping this part. That's it. We make it that far. We're going right to, what is this? Blah, blah, blah. We're going right to slide 13. This first one, a single server waiting line model, Poisson arrivals, exponential service. This is that first one on the list. Blah, 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 blah. You read that one. Here's your 2 important symbols for all 4 of them. This represents the mean number of arrivals per time period. It's the rate of arrivals, not the time, the rate of arrivals. This symbol is the mean number of services per time period, the rate of services, not time. Both these symbols represent the rate. So if you have that symbol with something, it's probably talking about rate, not time. How many per unit of time. Now, this is the story. These are your calculations. We're coming back. Where's the story? Where's our story there? Pass it? Blah, 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 blah.
What was the second one representing?
The mean service rate. The mean number of services per time period, which is service rate. it's the Burger Dome question. Let me see, does it talk about how many, let me get to, must be way back here. Blah, 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 blah. Okay, you ready? Burger Dome analyzed their data, and they realized their customers are arriving and concluding that the arrival rate is 45 customers per hour. Time or rate you just read? That's right. I've heard it, two people say it at least. Rate, rate. It didn't say it takes 45 minutes, it didn't say it takes 3 minutes on average. It gave you how many per a time interval. Now, I want to make sure you don't see things as a curveball. If the overall question says, we want to know the probability of blah, blah, blah for every half hour, the probability of this or that per half hour, you've been given a rate, but your rate is per hour. You've got to convert your rate now per time interval you're being asked about. So what would you switch the 45 to if you're being asked about a half hour? No. Say it again. Yeah, what is it? What is half of that? 22.5 would be the rate of arrivals, because the overall question is going to be maybe about a half hour interval of time.
You could just change 60 to 30 and get the same thing, right?
Where are you getting 60?
60 minutes to 30 minutes. 45 customers divided by 30 minutes.
Well, hang on, this is we're trying to get to a per minute rate here. I wanted to prepare
my
you
bad.
for a 30-minute rate. So now, this whole problem wants to talk about the rate per minute. What's the probability of arrival per minute? 1 minute, 2 minutes, 3 minutes. So you got to now convert your rate, even though you're given a rate, you got to convert it from 60 minutes to 1 minute. Just like you just did in your mind with 30 minutes, you said, oh, 30 minutes is half of an hour, so half that rate. Well, 60 minutes per minute, there's 60 of an hour, so you need 1/60th of that 45. So 45 divided by 60. The average arrival of customers at this Burger Dome is 0.75 per minute. Now we took it per hour and made it per minute. So if we're calculating this, the question's coming, it's going to say blanky blank per minute. You got to make sure you use the rate per minute. Where's the service now? Probability. See, this is the part. This is at the end of the chapter, because a lot of people find this really hard. So, blah blah blah. Where's my service now? Here we go.
Don't like that?
I can't remember where the service is, but it looks like it's. Oh, here we go. And Burger Dome did a study order fulfilled process, and they found that a single employee can process an average of 60 customers' orders per hour. Time or rate? Rate again. And it happens to be 60 per hour. But the question coming is going to be per minute. So you got to take 60 divided by 60 minutes. That's 1 customer per minute on average. Is that right? So now we have a service rate and we have an arrival rate. Arrival rate is this symbol. Can everybody see this? Equals 0.75. This symbol equals 1. And those are the two numbers, all you need to calculate all 6 of the characteristics of this problem now. And when I say the 6 characteristics, you get your list of things. Here they are. This is what you're expected to be able to calculate for every one of these 4 models. The probability that there's no units, which means customers, that there's no units or customers in this case in the system. Meaning the employees are twiddling their thumb, there's no one to get an order from. The probability of none in the system. Now think about a manager who can get that number. If someone says, look, I know how to calculate this. You're a new employee. You can go to your regional manager. You're managing 10 of these. Your regional manager has the whole state. You said, look, I can calculate the probability that there's no units in the system, that our employees are going to be twiddling their thumbs. And managers use this information to change the schedule. We don't want to waste money on providing customer service to nobody. So maybe we have too many employees working. This is what all of these are about, is are you scheduling the right amount of employees for every situation? And when you get into business, you're going to find out. They aren't working out schedules for, what are they open from 9 in the morning till 9 at night, 12 hours. They look at the schedule for like every 2-hour intervals. And they want to know, what's our probability of this happening in these 2 hours? What's our probability of happening in these 2 hours? And so on. And then they're adjusting the schedule, they make the schedule up to provide the perfect customer service, to not waste money. This is all about not wasting money. You change the schedule in order to have the right amount of customer service, to maybe keep this probability low, but to not have this probability go too high. What's the problem? This sixth one is the probability that an arriving unit, a customer walking in, will have to wait. Now, Burger Dome, we all expect to wait when we walk in a Burger Dome. We expect to wait. You know, there's probably 1 or 2, and there's always more people there, which is fine. And you take that into consideration. But if you do the math on this, and this probability is like at 90%, you're going to have a customer wait, and another customer wait, and it's going to be building up so fast that people back here are going to be leaving, going somewhere else. And that's why you have to keep track of this. Because if you have too few employees scheduled, and you knew this number, then you're going to lose customers, and you're going to lose revenue. And good faith. That's a big cost. Man, I went there, I'm not going back. I waited for 20 minutes and couldn't even get my order taken because of this. So these are the important ones. Now, they're calculated slightly different for each model. So for this first model, which is single channel Poisson arrivals exponential service, here are the calculations. And it's also on page 466, which I really like the book calculations, but here they are. The first one said, to get the probability of no units in the system, it would be 1 minus your arrival rate over your service rate. What's the probability of no customers there and the employees we schedule are twiddling their thumbs and they're playing games with the ketchup? What's the probability? Look, fake blood. Your turn. Come on. What's 0.75 divided by 1? 0.75. 1 minus 0.75. What do you get? 0.25. Turn it into a percentage. There is a 25% in this particular setup for Burger Dome that the employees are doing nothing. And that's not bad. But if your regional manager says, get that down to 10%, then you have to adjust your schedule and get it down to 10. Let's go to the next one. The average number of units in the waiting line. Now, Burger Dome, we know we're probably going to have some people waiting. But if that average number is too large, we didn't schedule enough employees. We need to make sure we have enough employees to have the average number of units waiting be within a certain range. And that's what you do as a manager. You would take the arrival and square it, 0.75 squared, 1 times 1 minus 0.75, so that'd be 0.25. So I have whatever that is squared, divided by that, and then you have your average number. All right, we're not going to calculate all these. I just want to show you how it's done. They're not that hard. And I posted, I posted an Excel spreadsheet that will do all these calculations for you, but you need to click in each of these boxes and see what's going on, how it's done. These will be exactly set up as you see on that PowerPoint. So what I'm going to do now is I'm going to plug in the arrival, 0.75, and plug it into service as 1, and we're going to see what all of our numbers are. %25 chance that there's no customers there and our employees are twiddling their thumb. I can't. Give me the average number. Average number is that the second one? Somebody got the list? No one has the list. No. Okay, here. There we go. Here. Boom. Then we go here. Wrong one. Here. Then we go here. All right. The probability of no customers there. Our employees are doing nothing. 25%. The average number of customers in a waiting line is only 1/4 of a customer. Yep, that looks pretty good. That's really less than I expected. The average number of units in the system are 3. In the system means they're there, they're being waited on, they're waiting for their order to be given to them, something like that. That's at 3. Now these 2 are the hardest ones. These next 2 have to do with time. The reason it's hard is a lot of people forget that these 2 will always be expressed in whatever unit of time these represent. Now this is 0.75 per hour. This is 1 per hour. So these are hours. Get it? The average time a unit spends in the waiting line, that can't be hours. What is going on? 3 units of time. Is 0.75 hour? It's not, is it? The question has converted to minutes. You have to change the words based on whatever problem you're doing here. McCarthy? Stop. Now, the average time a unit spends in the waiting line is 3 minutes. The average time a unit spends in the system, 4 minutes. Again, these two time ones always represent the amount of time that your arrival and service per time. If it's per minute, these are in minutes. If this is per hour, this is in hours. The trick is, a lot of times, these will be per hour, and these will be per hour, but it's asking you the average amount of minutes. So if this right here, the average time a unit spends in the waiting line is, I'm going to use like 0.2, because we ended up putting hour per hour numbers here, but it says how many minutes is the average time a unit spends waiting. But you're looking at this, and this is how many hours. You're going to have to convert this to minutes. So 0.2 times 60 minutes an hour equals, what is that, 1.2 minutes? 1.2 minutes. Or is that 12 minutes? That's 12? 12. Thank you. 12 minutes is the average time if this is 0.2, and those have been entered as hours. We get it?
So the 0.2 is the...
This is an imaginary, if these were hours and you happen to get a 0.2 right there, or right there. And the question says, what's the average time a unit spends in the system? Or what's the average time a unit spends waiting in minutes? You've got to realize, oh, this is in hours because I entered these per hour.
Oh, yeah. So
And you need to say, well, it's going to be like a real small number, point something usually, because it's in hours. And then you got to multiply times 60 minutes to figure out how many minutes that represents instead of hours. All right, we kind of fast. And then this last one, the probability of an arriving unit has to wait. This arriving unit has to wait is talked about, I've experienced with companies I worked with when I was a consultant. That one right there, the probability of arriving units having to wait, right, is probably the one we talk about the most. Because at this time, we're talking about the late 80s, 1980s, you weren't born. Was anybody born? I'm sorry.
You're talking about the
Thank
bath?
you. Thank you.
You're
Huh?
talking about when you were working at the bath? Like
No, I worked for this consulting firm, and I was an analyst, and I would travel all over. I'd fly out Sunday night, and they have to go through a company's, all their financials, to try to pinpoint where they're wasting money, where they're throwing money out the window. And sometimes we'd be talking about the waiting line. I did a restaurant in Detroit, the yacht club, I can't think of it, Detroit Yacht Club. That was a perfect example where waiting lines were involved. And we would talk about, is this too long of a wait? Is this too short of a wait? You know, and this is what's talked about. What's the probability of someone having to wait? Customer service was such a big deal in the late 80s that it was, we got to provide better customer service. We got to provide better customer service. They felt, a lot of companies said, this is the way to keep the customers, to keep the customer service. And to keep customer service, you would want that to be as low as possible. The worst way to offend a customer is having them wait too long. And so that's why this was talked about so much in the late 80s when I was traveling around. Right there. How do we get that down? You know? All right. What we do is we provide another service channel. And providing 2 service channels instead of 1, we've got to go to multi-channel to figure out the parameters. But you'll see the probability of an arriving unit having to wait goes way down because now there's 2 service going instead of just 1. And that is the #1 way to bring it down. And then you'll say, somebody will say, a manager you work with will go, well, then let's get 3 services. Let's just get rid of any wait. There's now, the curve always looks like this. You're wasting money because you don't have enough service channels and people are leaving because they're waiting too long, wasting money. You're wasting money because you have too many channels and nobody's waiting whatsoever, but you're wasting money because they're sitting around doing nothing.
That would help the probability.
You gotta find the sweet spot. That sweet spot is where a customer's, or where a company is not wasting money. They figured out how to have the right amount of employees or channels providing service to keep that probability of waiting down, while at the same time not throwing money away by over customer service or providing too good a customer service. Companies have me come in back in the late 80s because they were not making as much profit as they should. And in many cases, they were losing money. They're looking at me as their last hope. They're praying to God, I'm going to figure out what the heck's going on. Why are we losing money? We got, 20 million in sales and we're losing money. How can this happen? And I always went to the financial statements. And I go through the last 4. And something's going to jump out at you because you're working out the percentages. Well, 3 years ago, the employee cost for providing service was 20% of revenues. The year after that, it was 21%. But this year, you're at 40% of revenue being spent on your customer service employees. And that will jump out at me. And then I start investigating what's going on here. Why is such a large percentage compared to revenues happening with the customer service employees? There's possibly money being thrown out, and that's why your bottom line, your profit, is not what you expect.
That circumstance you said there, would it be that 0.25 up there?
That
If it
one,
was split, if it said 0.75.
if that one, that's the other end of the curve, where they're throwing money away because,
I was saying if that 0.25 and that 0.75 flip, that's that opposite end,
That's
the
right.
other, right?
That's right. And these are always the opposite of each other in this particular model, not all of them.
Right.
These are always the opposite of each other in this model.
Gotcha.
All right.
Love it.
Gosh, I can tell I should have another example right now. You can feel it. Let's go here. Let's go here. You ready? All right. You decided that, hey, what is this? Are we on? What is this? Man, these modules. Here we go. If you're not using Excel and you want to use the software, or you got to be prepared to at least analyze the software output, or the Excel output, or the Excel spreadsheet when you set it up. But the module is 9 waiting lines. You go here, we'll call it a new one, and you have all these choices. We're only doing 3 of these because 2 of them will use the exact same one. So only 3 of these. Here's Poisson arrivals, exponential service. That's for the first 2, single channel and multi-channel. Poisson arrival, exponential service. You would use that one. The next one down, arbitrary service 1 channel. That's our 3rd one right there. 1 channel, arbitrary service. Deterministic is another word for constant. So that 3rd one down is our last one. We're not doing these last 2. So do not accidentally click on those. We're not even doing those this semester. In operations, you may be going this far. I can't remember. We have a new teacher for it, so I'm not sure. But we're going to do these 4 to prepare you. So let's say we're doing this one, the 0.75 and the 1, but we're not doing the problem we just did. You just decided that we're throwing money away by not having enough service stations. So you decided to add an employee. Let me see, we got to look at, you're going to add another employee to see what effect it has, especially on these probabilities. We want to lower our probability that someone's going to have to wait because we think that's poor customer service in this particular business, whatever it may be. So, even though it's going to cost us a little bit of money because this will go up, which means we're going to be paying employees that are doing nothing a little bit. So we go over here and we say our arrival rate was 0.75 per minute. Our service rate, again, is 1 per minute. And we are now, instead of 1 channel, 2 channels. Here we go. Boom. What's the probability that a customer may come up and have to wait now, which used to be 75, 25%, 75,
It used to be 75%.
75. It was 75% chance. We felt that was too much. We were trying to provide better customer service. We added a station. Our goal is to get that probability of a customer having to wait too long down. What's the probability a customer will have to wait? We got it down from 75% to about 20.5%, 0.2045. Look at the time. Whoops, I forgot which one's. The average time a unit spends. Average time a customer spends waiting. Before we made this change, the average time a customer spent waiting was 3 minutes, and we decided that was too much. This is why we added the second channel. And now the average time a customer has to wait is how many minutes? A 1/16 of a minute. Not even a half a minute. That's how much better customer service just by adding this one station. Now we got it to 2 is going to do.
But now it's almost a 50-50 shot. You're paying people to do nothing.
But now, customer service was so important to us, this particular business, that we're okay with that. But let's see what happens.
It's a good job to have, right?
Let's see what happens if we add 2 more customer service stations. So now we got 3 people handling the situation. All right? And you look here, and you go, wow, the probability of an arriving unit, we took it from 75 down to 20.5, I think it was. Now there's less than 5% chance. And I can't tell you, there's many businesses who said they don't want anyone waiting, and they want their probability of a customer having to wait to be less than 10%. That was a very common goal for a lot of companies. And some even said 5%. This would meet the 5%. I'd say, well, here you go, based on your average arrivals, based on your average service for each one of the people who provide service or machines. If you want to get it down below 5%, you need 3 stations. Go ahead.
In this, like when you review that, would it be usually a 50-50 shot they'd be sitting there doing nothing? Or would it not normally end up that way?
No, these are pretty close to, during certain periods. You have to almost calculate this for 2-hour intervals because the arrivals change based on the time of day. Especially a restaurant, burger dome, fast food. You got a bunch of people coming in for that breakfast thing. You got a dead period. You got lunch. You did a dead period. You got dinner. Dead period. And then after the bar, crazy people. And you get those late night sales, right? And so you're adjusting your schedule. You're calculating this for each one. You break down. You say, well, every Wednesday lunch is about this many people. I've been at times where I have to look at the security footage on in fact, it was VHS. And I'd have to watch the security footage to see what the average arrival is, or the average service. And you're going, and in statistics, every time you're trying to figure out the average or something, or calculating anything in statistics, which is what this is all about, you must have at least 30 in your sample, period. Tell me you heard this in statistics. Anybody hear this in statistics? 1, 2 people? 3, 4, 5, you must have at least 30 in your sample. Many companies do quality control in manufacturing. And if any of you hooked up with manufacturing companies, there's going to be quality control involved. And statistics being used. And they never pull out every item being made by those machines. They pull out at least 30 of them. And when you go to make that delivery to a company, and they found in your last delivery that you had some that were not good quality, they're then saying, don't leave, and they're quickly pulling out at least 30 and measuring whatever needs to be measured to make sure that the batch is good. And if you go less than 30, your calculations are not going to be as accurate. But what's happening here is that when you're figuring out the arrival rate and the service rate, if you have to look at a film or you have to sit in a booth and watch, or however you do it, you need to calculate that same time period, that same day, to get the true arrival rate for 30 of them. And you'll know the arrival rate on Wednesday at lunchtime. And you'll know the arrival rate on Fridays after the bar closes. You'll know, as long as you did 30, so you go back in time. Many restaurants have receipt machines that will tell you the timestamps on there, what was bought, how many people, and you could just go through those receipts all the way back to get to that rate of arrival. That's how it's done in real life. That's how I had to do it. But for this class, you'll always be given the arrival rate. You'll always be given the service rate. You have to come up with these 6 numbers. And then maybe be asked a question about these. You know? Where we're heading with this is we're going to take it a step farther. And it's called the economic analysis. What the economic analysis does, it takes what is the cost to add another service. Meaning is, Burger Dome, we got one person taking orders. If we decide to put another person here to take orders and another cash register, what is our cost involved? And if we're giving benefits, you've got to add the benefits in. Well, this person, he or she, is making $10 an hour, and there's no benefits involved because we're Burger Dome, and they only work about 29, 30 hours a week. So the only cost to add a service station will be $10 an hour. And we'll enter in the economic analysis that you'll learn next week for the service, if we add a channel, $10 an hour. Then there's what's called a waiting cost. It's Burger Dome. If a customer's waiting, what costs are involved? Especially if they're waiting too long in a lead. So it's a tough one, because people who walk in Burger Dome, they expect to wait a little bit, right? But if you have them wait too long and they leave, there's a cost involved. Or even if they stay, but they feel bad about the company because they had to wait so long, there's a cost involved. That's a very hard thing to calculate, but you'll always be given the waiting cost, and you'll always be given, in this class, the cost per channel. And you got to take those two numbers with that arrival and with that service, and you will learn how to calculate the total cost for everything per hour. And you'll put in 1 person taking orders, and then you'll change it to 2 person taking orders. There's your total cost. 3 person, 4 person. And really, this represents that total cost that we're getting to. Let me put the graph here. And if there's too few people, the waiting cost is so high because you don't have enough people providing service that your total cost is way up here. And you have too many people, your waiting cost is way down, but your service cost is too high. And that economic analysis will get you right here. And when you find this, I'm scheduling 2 people on Wednesday afternoons at lunchtime every Wednesday until we see that there's a change taking place, and we do this again to see if the schedule needs to be changed. And this 2 hours over here, this 2 hours. And you go, well, this person has to work 6 hours, so if I need this many, remember that problem on the quiz? You have to have a certain minimum amount, so you're working out a schedule because they're there for this 2 hours plus this 2 hours and maybe that 2 hours, but another person's arriving, but you've got to fulfill the minimum. This is combined with this. It's about scheduling the right amount of employees so that however many units of time that they're there, and they're crossing paths, one's just arriving and one's still there for their last little 2 hours, you want to make sure all those minimums have been determined based on this. If it's a waiting line company, if the company has a waiting line, the minimums have been based on this calculation, the economic analysis, if you're based on how many provided service stations you have. And once you find this, you now know that's the amount of employees on my schedule for that period. Then you do it again. You find this, that's the number of employees on my schedule. Anybody work at a bank or a credit union now? Okay, this is exactly how tellers are scheduled. They know, a bank and credit union know exactly how many people arrive during a certain time period. Banks and credit unions I work with, sometimes they're using 2-hour intervals, sometimes 4-hour intervals. They're saying that for this time to this time, this is our busy time, and so we always have this many customers. And they know when it starts to slow down, so that would be another interval of time that they'll figure out, well, this is how many we need for this time period. And then they work out the schedule using linear programming software to say, okay, now you're scheduled from here to here, you're scheduled from here to here, and we know that you two are going to be there at the same time for this many hours, but it's right during the busy time. So, you've learned now, single channel, points on arrival, exponential service. You've learned that multi-channels, almost just like it, at points on arrival, exponential service, and that a single channel in real life as a manager turns into a multi-channel if you find that you're not providing good customer service. But here is how the multi-channel is calculated. You know what I'm going to do? I'm going to jump We're going to look at these formulas now. Going to page 471. On a multi-channel, please tell me that's turned on. On a multi-channel, the formulas are not the same. Tom, did you want, Tom wants it? Tom, you want it?
Yeah,
Man, oh man, thank you.
no problem.
We release this up, will you?
Okay.
Yeah, pick this up and do it. See these formulas right here? Let me get them on here. Come on. The probability of no use in the system isn't just 1 minus arrivals over service. It's this. What? 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 This. And the average number of units in the waiting line is this. Right here. Look at the same variables. You got your arrivals, you got your service. The only other variable you see is K. K represents the number of service stations or number of service channels being provided. And so someone will say, well, let's try 2 channels. This is multi-channel, but you make K a 2. Then someone will say, well, now let's try 3 channels. Same formulas, but K is now a 3. I'm not going to expect you to hand calculate this. I'm going to show you a shortcut for the first one right now. P sub O. The average number of, the probability of a unit, no units there. And your employees are twiddling their thumbs and spitting at each other. That one. And let's just use the same example. We've got arrivals coming at 0.75 per minute. We have service coming in at 1 per minute. Or we could go to hour. I can't remember the hour, so I guess we'll stay at that. To calculate this, do not try to do this calculation. It will just take you too long. All right? Instead, calculate this. Your arrival rate divided by your service rate. And find that number. Which happens to be, in this case, 0.75. 0.75 divided by 1 is 0.75. Once you know that ratio, you can go to this table on page 473 and you find 0.75. And when you find 0.75, it will give you that P sub O, the probability of no units in the system, and your employees are twiddling their thumb, if you have 2 service channels, 3 service channels, 4 service channels, or 5, every number is right there for you, based on the fact that arrivals are 0.75 and service is 1 per minute. So we'll go, 0.75. We're thinking about adding a second person. So if we add a second person to this burger dome, our probability of no units in the channel and our employees are bored will be about 45.5% chance. Now, if you recall, on this one's on 473, the formula's on 471.
What does M represent over there again? Your 1, where's that 1? 0.75 divided by 1, what is the 1?
Oh, the 1 was the service rate.
Service rate.
Right, the Burger Dome said, they did it in hours. Someone help me out. Well, this was 60 per hour, I know that. But what was this one, this 0.75 per hour? It was less than 60. Was it 45?
45 out of 60.
Was it 45? So this was 45. So let's do it again now. 45 per hour divided by 60 per hour. Oh, man, it's the same number, 0.75. So look at 0.75 again. We get the same answer. As long as your arrivals and service are in the same interval of time, you'll always get the same answer.
It's not the Z-table.
No, it's not Z-table. This is the probability that no customers are good, that no customers are in the system at all, and your employees are doing nothing that are providing service. Is that? Now I want to show you on the software. Hang on. Right here. Come on. I want to go back to edit. What was that probability at 0.75 if we had 2 we had 2 service stations? What was that probability? 0.4545. You look on the software. You put in 2 customer service stations. 0.4545. Same answer. And it's right there on the table because it would take you way too long to try to calculate this right here. But here's the deal. When we get to economic analysis, the only way to do economic analysis is you have to get this number on multi-channel exponential service. And the only way to get that number is you gotta have this number. And the only way to get this number is you gotta have that, which is the first one. So you, if this was a problem that you determined that you're gonna have to do an economic analysis and it's multi-channel exponential service, it's the only one that's multi-channel, this is how you're recognizing it, there's more than one service place, then you've got to say, I'm going to get the arrival rate, 45, the service rate, 60, both in hours, divide it, I get to 0.75, I go to that next page, I get that piece of O off the next page, I plug that in right here, this K is a 2, that K is a 2, that arrival is a 45, that service is a 60, and you can calculate this. The only thing I need to refresh your memory of is factorial? Help me out, is that factorial symbol? Is that what it stands for? I can't remember the name of it, but here we go. Here's your review. 4 factorial. That means you go from that number down to 1. Multiply. 4 times 3 times 2 times 1 equals 4 factorial. 3 factorial. 3 times 2 times 1. 8 factorial. 8 times 7 times blah, 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 to 1. That's what factorial means. Right here, 2 service station minus 1 is 1 factorial. 1 times 1 is 1. So now that part would be a 1. Here's the only trick to factorial that everybody goes, I can't, it just doesn't make sense, but this is true. 0 factorial is not 0.
1.
It's 1.
Really?
Yeah.
Hey, you see your kids.
Everybody hear me? So if you have, you wouldn't do this if you only had 1 station there, because you'd be single channel then. But if for some reason, I don't know how it could happen, but 1 minus 1 factorial would be 0 factorial, it's still 1. Factorial is something you forgot completely about, like most people do. Take some good notes to refresh your memory so you can calculate this. Then you calculate that average number of units in the waiting line. And you take that number and use it to get this number, the average number of units in the system. Because you must have the average number of units in the system to get that cost, to figure out how much it's costing you as a manager, wherever that may be, you have to have that. And you're using that with that waiting cost, with that cost to add a station, and the economic analysis. This is going to be faster, right here. Here we go. Hang on, where is it? Already pass it?
Yeah.
Did I?
Wait, wait,
Down there.
I don't know what you're for.
The economic analysis. All right, let's do the PowerPoint then. Who's got their foot? All right, here we go. Here it is. The economic analysis is going to be, well, let me say after all of these. It's going to be the cost of each service times the number of service channels. It's going to be the cost of each service per unit of time. We're coming to this on Monday, so you don't even have to take notes. Times the number of channels you're evaluating, plus the cost of waiting per unit of time times that L. You've got to have that L. A lot of these problems in your future are economic analysis. Would it be a better decision to have 2 employees provide service or 3 based on your cost per unit of time? So when you're getting to these, all you got to do is get to that L. You don't need to calculate any of the rest. To answer an economic analysis question, once you get to L, that's all you need to answer the question. But you've got to get to each of the steps that get to L. So even though there's 6 of them, thought I was on the same page. Yeah. Even though there's 6 of them, there we go. You only have to find the answer to those 3. You get this off out of the table, you calculate this, you can have this all set up in Excel and just plug in the 3 different numbers. And then you get this. Now you can show your work for economic analysis and tell me, would it cost more to have 3? Would it cost more to have 4? That's the type of question you got in your future.